Good afternoon, everyone, and good morning to Professor Dennis Meier. So today, as part of our functional oxides group, the Center of Excellence seminar series, we have Professor Dennis Meier from Norwegian University of Science and Technology delivering a lecture on improper ferroelectric domain walls for next generation nanoelectronics. So the functional oxides group is a special initiative we started almost 2 years back, where a few of us who works in oxides got together and created this center. So we are in a critical stage. We will know whether the further funding will happen for the 3rd, 4, and 5 years. We have been having this seminar series, and we are very delighted to have you here as one of the distinguished speakers. So I will hand over the session to Professor Prashanta Mudali to formally.
Link পাঠালাম.
What is that?
There was some noise, something else. It is not.
Yeah, I will hand over to Professor Prashanta Mudali to formally introduce the speaker. Thank you.
Okay, it's my pleasure to introduce Professor Meier. So let me give a small bio of Professor Meier. Professor Dennis Meier is a full professor at the Department of Material Science and Engineering at the Norwegian University of Science and Technology, where he is heading the functional topological systems team, and he is associated member of QSPIN, the Center of Excellence for Quantum Spintronics at the Department of Physics at NTNU. Meier received his PhD in 2010 from University of Bonn, Germany. He worked at UC Berkeley, US, ETH Zurich, Switzerland before joining NTNU. He is the Vice President of European Magnetism Association and serves in different positions, including the Advisory Board of NTNU Nano, the Quantum Oxide Research Online Meeting, the European Meeting on Ferroelectricity, and the International Conference on Electroceramics, the International Symposium on Ferroic Domains, and the European Conference on Application of Polar Dielectrics. Furthermore, Meier is editorial board member of Communication Physics, Nature Springer, and the Journal of Electroceramics Springer, and elected member of Royal Norwegian Society of Sciences and Letters, and the Norwegian Academy of Technological Sciences. Some of recent honors include awards from German Physical Society, Norwegian Academy of Science and Letters, and the ERC Consolidated Grant. Now I will hand over Professor Meier to start his presentation.
So thank you so much. It's really my great pleasure to contribute to your nice seminar series, and to hear that you have this Center of Excellence there going in this direction. And I really wish you all the best for that, and the good luck for the future. I hope that some of the topics I picked for today's talk are interesting for many of you, and I'm already looking forward to having a nice discussion with you afterwards. The title, as you can see, it's Improper Ferroelectric Domain Walls and how we can use them for nanotechnology. So it's clearly fundamental research with a technological motivation. What can we do with these objects in the future? How far can we go? But as you will see, and several of you will know if you are following the field, a lot of it is still fundamental science. And there is a lot of physics to explore, techniques that we can really utilize at the boundary of what's possible nowadays. So I think just because of that, the new emergent physics, the technological challenges to measure these objects is already by itself something that is for me very, very intriguing when it comes to these domain walls. Before I get to the topic, I thought it might be nice to briefly show you where I'm sitting right now. You already heard that I am here in Norway. Can you see the you can see it like that, I guess, right? The red pointer. Yes. So I'm sitting here in Trondheim. It's not too far south of the Arctic Circle. I just mentioned in the beginning that temperatures just went below 0 here, and it's starting to freeze. Our university is close to the center. You see it here on the right-hand side. It's on a small hill so that we look a little over the town towards downtown. And NTNU is actually the largest university in Norway with more than 42,000 students. So especially when you take into account that Trondheim only has 200,000 inhabitants. It's quite a student city with a lot of young students coming here from around the world to study. So really nice atmosphere. And if you haven't been here yet, I can only recommend to come by and visit us. During the winter, we of course get a lot of snow here. You see here one picture from one of the more modern buildings on campus. You see also here a picture of downtown. We have these nice wooden houses, which really gives you the impression you're in the middle of Norway as you expected when you visit downtown. And on the right-hand side, you actually see the main building of our university. That is what you see when you enter the campus. And if you're lucky during the winter, you then have the chance also to see northern lights here. That can be really spectacular. And I'm now living in Trondheim for 6 years, or in Norway in general. And no matter how often that happens, it's always really nice to see that. So this is just to give you a little bit of a background or an idea where I'm sitting here at NTNU and how it looks like. And with this, I would then now like to move on towards the science part. In our group, we are interested in functional topological systems, investigating electric and magnetic materials mainly. And what we are really interested in is defect structures, like you can see here, for example, on this image. Whenever dislocations like that, for example, are formed in a magnetic or an electric system, you have a completely different environment than within the rest of the material. The symmetry is different, the chemical composition is different, and all that gives rise to new functionalities. And these can then be used in next generation electronics. That is one of the ideas. I already said they give rise to very interesting physics. And we try to study that and understand what's going on at the local scale here using a lot of different microscopy techniques. We are specialized in scanning probe microscopy, which we use to look at domain structures, domain walls. We have microprobe station. We use the FIB ion beam to nanostructure our materials, to make device-like structures, as you see here on top, where we put then lamellas onto electrodes and see how they react to certain stimuli. We also do TEM investigations to look at the atomic scale, 3D imaging by atom probe, and every now and then we also go to the beamline to do some PEM and LEAM measurements. But the instruments would all be useless without the nice people running them and our specialists in the team. So here you see a snapshot of the group beginning of the year. So we're usually around 10 people, sometimes a little less, sometimes a little more. And they are working on the different instruments and collecting the data. Most of the results you will see today were collected by Erik Röde. He was one of our PhD students in the group, Caspar and Chia Li. So they are the main players within the ferroelectric domain wall business, and they contributed to the research I'm going to present today. Also, let me briefly acknowledge some of our collaborators. We have close collaborations with Julia Mundip, who is providing sometimes samples for our studies, or in the past also did some high resolution TM measurements for us. Andres Kano, Max Stengel, and Konstantin Shapovalov, they are helping with the theoretical analysis of the results and the modeling. And then we get samples from Tali Roshak and Zebu Yan and Edith Bure at UC, not UC Berkeley, sorry, LBNL in Berkeley, a little uphill from UC. And we also recently collaborated with Brian Huey regarding some 3D imaging I would like to talk about today as well. Okay, so much for the very general introduction. Then let's come to functional oxides, the topic you are all also interested in. I apologize if that's a little too simple for your background, but I think it's always good to start on a general basis so that we're all on the same page and you understand later on why I'm so happy about some of the mechanisms we are finding. So in general, when we talk about strongly correlated electron systems, what we have in mind is materials where you cannot think about the charge carriers anymore as the individual particles, like in the Drude model for a metal, for example, where you think about the electrons as spheres running through the metal. In a strongly correlated electron system, it's really important what you do to every single electron, because that can have a huge impact on all the rest of the material. And that applies to the magnetic properties, the conduction properties, ferroelectricity, and so on, as shown in this graph on the right-hand side. So the electrons, which we are playing with, they have the orbital degree of freedom, charge degree of freedom, and the spin degree of freedom. And that then gives rise to different functional properties like superconductivity, magnetism, and ferroelectricity. And what's really important is that all these physical properties are directly related to the symmetry of a material. It is symmetry violations that determine the functional properties, which is summarized in Newman's principle, for example. So this fundamental correlation between symmetry violations and emergent properties, it's basically known all along. And this is why oxide interfaces are so interesting, because when we have an interface, you have a completely different symmetry than in the bulk. You have confinement effects, you have a different chemical environment. So interfaces are a really exciting tool to play with all these different functional properties, engineer new ones, or optimize them for certain applications. What I will focus on during my talk today mainly is this charge degree of freedom and ferroelectricity. But as I just pointed out, these properties are strongly correlated with all the other effects you can find, and we can use one to play with the other and vice versa. So interfaces is the direction in which I would like to go. And there are different types, many different types of interfaces we can find in oxide materials or strongly correlated systems. And here are three of the examples that are recently studied very heavily or have been studied. On the left-hand side, you see the example of an oxide interface, a hetero interface, illustrating the case of LaOSTO. This was the exciting example discovered about 10 years or a little more than 10 years ago now, where you bring together two insulating materials, LaOSTO, and at the interface, a 2D gas forms. You have enhanced conductivity or even superconductivity. So emergent new properties right at the position of the interface. Then in the middle, you see another example, a twin boundary. Again, the atoms at the interface see a completely different environment than the rest of the material. You can get new functional properties that are not accessible in the rest of the system. And here again, one exciting example was a change in the transport properties I already mentioned. I will focus on that today. Eckhart showed I think it was in 1989, that these twin domain walls can be superconducting, very similar to the oxide interface in LaOSTO, or similar properties. And then last but not least, on the right-hand side, the ferroelectric domain walls, where we have a discontinuity in the polarization orientation. So again, a different state at the position of the wall and emergent electronic properties. Also here, we can have conductivity at the domain wall, even though the bulk is insulating, and much more. What really triggered the interest of the community was the spatial degree of freedom we have with twin boundaries and domain walls that's not available in artificially grown interfaces. So once we have a system like this, the state is set and we cannot really change that anymore afterwards. This is completely different with twin boundaries and domain walls. You can move them around and play with them even after material has been synthesized, so they are spatially mobile, which gives additional opportunities. All that was studied intensively over the last during the last decade, and it's now clear that whenever we have ferroelectric domains separated by a domain wall, that this domain wall can have completely different properties than the bulk, and that ranges from much more insulating properties to much more conducting properties. It can develop ferromagnetism in an antiferromagnet and much more. So it is almost impossible nowadays to list all the different interesting studies that were published. But what's really something I would like to point out is that also a lot of techniques were developed over the time that allowed us to, in the first place, to study these properties. Early on, people started to put electrodes onto the top of the domain wall and measured the transport properties, and then compared that to electrode pads sitting in the bulk to see that there is enhanced or reduced conductance. Of course, scanning probe microscopy became one of the most widely used tools, because you have this sharp tip and then you can measure conductivity, piezo response, and other effects on the walls. And then there are also some other ideas like extracting individual domain walls from the materials and contacting them to bypass some of the experimental limitations from scanning probe and, for example, do dielectric spectroscopy measurements in setups like this. I already said that there are many studies, and it becomes more and more difficult to name them all. That's why I put the reference to this book here on the right-hand side, to which many people contributed. And if you are interested, this is really, I would say, a quite interesting read to give you an overview and dig more into the details and the current state of the art of domain walls. The idea, of course, is then not just to look into the physics, but also to use the domain walls for applications. And again, that is something that came up as a fundamental idea quite early. Already in the 70s, it was proposed that domain walls can have different conduction properties than the bulk, and then depending on what type of wall you have, a negatively charged one where the polarization is facing tail to tail, positively charged one where the polarization of the ferroelectric is facing head to head, they should in principle give different conduction states and therefore allow to control conductivity. In the 70s, however, it was not really possible to measure that, so it was a theoretical paper with this was proposed, and the real breakthrough was then by Jan Seidel in 2009, when he showed that you can really write individual domain walls in between two electrodes. You can control the number and increase them from 2 to 4 to 6 domain walls, and that this really goes hand in hand with an enhanced flow of current in between the domain walls. You can then even erase them and go back again to a lower current level. So this shows that it's in principle possible to get multiple resistance states by playing with conducting ferroelectric domain walls. Over the time, it then became more sophisticated. It was shown that you can also change the orientation of the domain wall to get different charge states, or use domain walls to read out the polarization orientation in memory devices. What I would like to emphasize with respect to all these concepts is that it's really nice that you have these domain walls as rewritable entities and you can control conduction states, but it does not really represent a conceptual leap ahead with respect to the device structures, because you still write the domain walls into large devices. So you don't break the mold of these structures. You still have two macroscopic electrodes between you write the domain wall. So you do not really benefit from the small size of the object, because what's limiting your applications is the structure you're designing. So it's a nanostructuring determining the device size, and actually not really the atomic scale size of the domains. That's why I call these the classical concepts for nanoelectronics. They have a lot of advantages and show the potential of domain walls, but you do not fully exploit all the advantages like the size. A newer trend is then to use the domain walls themselves as the devices, to go beyond just enhanced conductivity, but use complex correlation phenomena that occur within the domain walls, and make devices based on that. Because if it is the domain wall itself that gives the functionality and you don't have to move it around anymore or erase it, then we can really go towards atomic scale electronics and test how small devices can become in the end. To illustrate this idea a little better, here the idea would be that I have different types of domain walls. I just call them now domain wall 1, 2, and 3. And I functionalize them in different ways. One domain wall could be a logical gate, another one could be a switch, a diode, and so on and so forth. Of course, at this point, this sounds like dreaming, but I hope that I can convince you in the rest of the talk that it is really feasible to mimic many of these functional properties utilizing individual domain walls. And then there are also first ideas now how we could afterwards wire them up, as shown here in the background, to really go from individual domain wall devices towards maybe more complex circuitry, and thereby mimic electronic components and circuitry at the local scale. So that is the dream we are following after in our group with some of our research, and also what I would like to discuss during this talk today: how far can we get, what is really possible in this direction. And this is then the outline of what's coming. In the beginning, I would like to give you a little more introduction to the domain walls in hexagonal manganites. That is the model system we are using. Then I will discuss in the second part how we are emulating electronic components at the nanoscale using these domain walls. And in the last part, I have to see how much time is left then and how fast we can go through that. But there I would like to show you some more recent results where we now go from 2D imaging at the surface really towards 3D imaging of the domain walls and utilizing that they are in a network within the bulk, and actually there's much more going on than we can see just at the surface. But let's get started step by step. Our model system, the manganites, it's no new idea that there are domains in this material. And actually, they were studied for more than half a century. What you see here is an early image of the ferroelectric domain structure in yttrium manganite that was obtained by chemical etching and then imaging the surface. And you see here that there are the brighter and the darker areas, and they correspond to the two possible domain states with polarization pointing either upwards or downwards. So we have a uniaxial ferroelectric with only two possibilities, and that you see actually already in this image. The material class then attracted much more attention again around the 2000s when it became possible to image these domain structures with much higher resolution. And what you see on the right-hand side here is a scanning probe microscopy image. And you see basically the same, but now you can resolve all the details and look much more into the local scale properties. For example, there are these 6-fold vortices that are forming, a lot of research focused on that. But for us, the most interesting part the domain walls that separate these really beautiful looking domains. Before we get to them, and also to explain better why the system is classified as an improper ferroelectric and why this is important for us, let's quickly look into the structure of the material. So it's a layered oxide system. We have these layers of rare earth ions, in this case yttrium. Then you have the manganese layers surrounded by oxygen bipyramids. And when the system goes from the high temperature paraelectric phase into the electrically ordered state, these manganese oxygen bipyramids start to, I don't know if you can see my picture, but I'm trying to also work with my hands here like in a normal talk. So these bipyramids, they buckle and tilt, and they can do that moving either towards an rare earth atom or away. And this at the end gives us the two domain states. So if they move or tilt towards an atom, this one is pushed upwards, and that's actually the situation seen on the left-hand side where we have this up, down, down picture. But they can also move in the other direction. This atom goes downwards. Oh, sorry for that. And then we have the opposite motion. And these two states then later on will correspond to the plus and minus domains. But at the beginning is a structural change that determines the domain structure. Nowadays, we can image that also with higher resolution. Here you see now the erbium atoms up, up, down, the manganese in between. And when we image larger areas, here it's a plus P domain state, you can see that there are different options. You can have up, up, down, up, down, up for these erbium atoms. And these states are all energetically degenerate. They all cost the same energy, which is due to the order parameter that's sketched down here. It has an amplitude and a phase that relates to this tilting and motion of the oxygen bipyramids. And you can actually then imagine this displacement here of the atoms as a sinusoidal wave. And then when you shift the wave by a certain amount, 60 degrees, you have at the end of the day the same energy state. So that's why these you have the 6-fold degeneracy. When you then do larger images, you can really see that all these 6 states are populated. You see them here now in order parameter space, written down as amplitude times cosine of the phase for the 2 order parameter components. And yeah, you see really all 6 states are populated. And in between, you also have some contributions. And that's actually not just noise. This is where the domain walls are. They have a slightly different symmetry. So they also show up here. And you already can see from that the atoms are shifted in slightly different directions, have a different symmetry. So they already show up here. What I would like to emphasize now, what I mentioned up to this point, is a purely structural effect. All this is geometry driven, and this structural order parameter is a symmetry breaking order parameter that determines the domain state. Ferroelectricity then only shows up as a secondary effect as a higher order coupling term. So that's the improper ferroelectric nature of the system. You have these structural changes, they determine the energy landscape, and only due to a coupling, a small polarization shows up on top of that. And that's really crucial because it means that the polarization has not much saying in how the domain structure looks like. It is already established, the polarization comes up and has to live with what's already there. And because of that, you don't see at all that it's a uniaxial ferroelectric. Actually, if you image the domain structure, you get images like here on the left-hand side. You see erbium manganite, piezo response force microscopy image, dark polarization up, bright polarization down, and it's fully isotropic. The domain walls are meandering around as if there is no preferred direction because of this improper ferroelectric nature. So when we now zoom in, we can find, because of that, all different kinds of domain walls. That's what makes it such a nice model system. We find sections where we have tail-to-tail configuration, negatively charged walls, head-to-head configuration, positively charged walls, neutral domain walls, and all that in the same material. Because of the charge state given by the polarization, these walls are expected to have different transport properties, and because of the stabilization through the structural order parameter, we really have robust quasi 2D semiconducting interfaces we can play with. That's why I'm so happy about this model system, and we are doing a lot of investigation on this one. You can do all these comparative studies within the system. Now, to bridge to the electronic properties, when we have these domain walls and you have at the tail-to-tail walls the bound polarization charges, you need to screen them. For the negative charge, what is happening is that the conduction band, the valence band maximum bends upwards and you create more holes. It's a p-type semiconductor. So here we expect enhanced conductivity, whereas at the positively charged head-to-head walls, the valence band maximum bends downwards. We have depletion. You don't want to have positive carriers here. The holes move away, and we would expect reduced conduction because we have less carriers. You see already that this band dips below the Fermi energy, but we come back to that afterwards. First order approximation, accumulation of holes at the tail-to-tail walls, more conduction, depletion at the head-to-head walls, less conduction. This is just the numbers. We have a carrier density of 2 × 10⁻⁹ in our semiconductor. This is what we can redistribute to the domain walls. And the domain walls themselves are really tiny objects with a width of about 5 angstroms. And that's what we want to use in our devices, that they are so small. But can we really see that there are these differences in conduction? Yes, we can. These are measurements from 2012. I recorded at that time together with Jan in Berkeley. And you can see that when we do atomic force, conductive atomic force microscopy measurements. So we scan the surface with a conducting tip and inject a current that will then spread through the wall and to the bulk differently. And we can really map out the conduction properties at the walls and within the bulk. You see that on the right-hand side, the domain walls are more conducting or have different conduction properties than the domains next to them. That's in line with what we've seen before. And when you then do really careful measurements, you can see exactly what I told you. We have insulating head-to-head walls where carriers, the holes move away. We have neutral domain walls where we just have the same status in the bulk. And we have conducting walls, the tail-to-tail walls, where all the holes will accumulate for screening purposes. And the conduction changes continuously with the domain wall orientation as control parameter. So this was kind of the starting point for looking into the domain walls as functional devices after knowing that they have these properties. And then we had the idea to use them to emulate electronic components, which I will now discuss in this middle part of my talk. So I just mentioned that we have insulating domain walls head-to-head and conducting domain walls tail-to-tail. Well, but if we ramp up the voltage and measure the whole thing at 6 volts instead of 2.5, you see that now all walls are conducting. And this is evaluated in a little more detail on the right-hand side. You see in the beginning, if I increase the voltage, the head-to-head walls are insulating, they're lower in the bulk, and then suddenly at a certain threshold voltage, they become more conducting. So there's a little more going on than the depletion and accumulation. You have this transition from resistive to conductive behavior. We then looked into that in a little more detail, and these are now measurements from Giulia Mundi. She did yields measurements right at the position of a head-to-head domain wall, and you see the spectra, comparison of spectra at the domain wall and the bulk here on the in the middle. You can already see that the manganese 3+ spectrum, model spectrum, nicely fits the bulk behavior, but there is a deviation at the position of the wall. Actually, on average, you have a valence state here of 2.8, which converts into an electronic charge, as you can see here on the right-hand side. And when you do the math, you see that this is equivalent to 0.09 electrons per manganese atom at the head-to-head walls. So there are some electrons sitting at the position of the head-to-head walls in our p-type semiconductor. And this totally makes sense with also the calculations I showed you before. The conduction band minimum dips below the Fermi energy. So we do not just have a depletion area of holes where it dips below, we have an accumulation or we have an electron inversion layer forming. And we then learn to do more careful conductivity measurements, and you can even see that then at the middle of the head-to-head walls. You see exactly the same profile here in the CFM scan. We first have the insulating area around the wall where we have the depletion, and at the core of the wall there is this electronic inversion layer forming. So you just need some higher energy, some higher voltage to also drive the electrons and get enhanced conductivity here, which you can understand in terms of a polaronic picture or averaging effects. Baseline is that you can activate and deactivate this electronic conductance that's shown here. We can now sit with a tip on top of the domain wall and then switch back between high and low voltages and repeatedly switch between resistive and conducting states. So we can use the domain wall as a switch, and the size of our switch is only limited by the contact area we make. So now we are really going into the direction of utilizing the domain walls here to control currents. And what's also important is that we do not just switch the current on and off. We actually have a qualitative change because we go from hole-dominated to electron-dominated conductance when we activate and deactivate this inversion layer. So that was the first example for really utilizing the walls, what functionality they can give to us. And the second one I would like to discuss is how we can use them to rectify currents. In general, when we bring together a metal and a semiconductor, a Schottky barrier is forming. This happens not just as the domain walls, that happens everywhere. And because of this contact, the Schottky contact, one measures an asymmetric IV behavior. So if I now go from negative voltage, for negative voltages, I would be in the blocking direction, for example, and for positive voltages, I'm measuring current. Yeah? So this is the standard behavior of a Schottky barrier. What's now special is when I look into the manganites or ferroelectric is that when I have a polarization out of plane that changes the density of carriers at the surface. It's illustrated down here. Whenever I have a polarization pointing into the material, there's a negatively charged surface. So in our case, we will accumulate holes to screen it at the polarization at the surface, whereas we have depletion when the polarization is pointing the other way. This will then, of course, modulate the Schottky barrier that is formed within the domains, and it gives rise to two different IV curves for the two domains. When you now apply an AC voltage, so you go back and forth, and you measure the averaged output, you would expect a higher current for this domain, for the minus P domain, than for the plus domain, right? Because the Schottky barrier is different, and by applying an AC voltage, the DC output should be different. That is well established, and you really see that when you now measure in this way, AC voltage applied to the back, we read out the average voltage, then the minus P domains are conducting more than the plus P domains at a 0.2 megahertz. What's now interesting is when I ramp up the frequency, you see that this contrast slowly vanishes, but a distinct contrast at the domain walls is popping up. And if you go to high enough voltages, you only see a signal at the position of the domain walls. Because we are averaging, that means that only the domain walls are now rectifying. You have symmetric IV curves for the domains. You short-circuited the Schottky barrier, and only for the domain walls, this Schottky barrier behavior remains, and we get only rectification behavior at the domain walls. This is now the signal as function of frequency. So we have a certain signal from the domain walls, and at a high enough frequency, this signal goes away because we have diode-like behavior only at the contact between our electrode and the domain wall, where we now have rectifying behavior. The rest of the bulk has symmetric behavior. Only here we rectify. So also in the AC regime, the domain walls have some specific property that we can utilize. And of course, that relates again to their charge state. We played the same game also for charged domain walls. Here you see again tail-to-tail and head-to-head domain walls. And if we measure their response in this AC CFM, how we call it, you see that we have enhanced conduction or enhanced signal at the tail-to-tail walls and reduced at the head-to-head walls. So if I now follow that again as function of frequency, you see that the frequency drop for the more conducting tail-to-tail walls occurs at larger frequencies than for the domain and much larger than for the head-to-head. This can easily be explained by their intrinsic conduction because the drop frequency, that's also known for bulk systems, is proportional or depends linearly on the conductivity. So if the conductivity of our tail-to-tail wall is higher, the drop frequency is higher than for the domains. And if the head-to-head walls have a lower conductivity, their drop frequency is lower. So all this is fully consistent and shows how we can utilize the walls for rectification purposes. Different walls, different frequencies. But it also has other interesting consequences because it's not as simple as shown here. If you have a Schottky barrier on an oxide, it also is voltage dependent. So the voltage, in addition to the intrinsic conductivity, can modulate the barrier. This is seen here. We now look at again at a tail-to-tail domain wall with an AC drive voltage of 0.4 volts and a certain drop frequency. If I ramp up the frequency, the drop frequency becomes higher and higher and higher. You see that here on the right-hand side. The drop frequency increases with increasing AC voltage. Same for the domain, but all the time we stay above the domain. So the frequency below which rectification occurs is controlled by the domain wall charge state and the applied voltage. So that's illustrated here in this equivalent circuit model. We need to take into account that also the barrier is voltage dependent, and it decides where we go from sinusoidal to rectified currents. And that we can utilize now. That means that we do not just have rectifying behavior at the domain wall electrode interface. We can even gate that. We can measure that at low voltages. Then there's no rectifying behavior at the wall. Everything does the same. If we go larger voltages, only at the position of the domain wall rectification occurs. And we can again do that back and forth repeatedly and switch on and off our rectified diode-like behavior of the wall. So to summarize this part, we now have different functionalities. Domain walls can be digital switches. They can be used as half rectifiers. Question remains, how can we wire them up? This is actually a topic for a talk by itself. I just want to briefly give you the idea how we are working towards that. We recognize that in our materials, we can use the tip of the AFM, apply a voltage, and then write conducting wires, as you see on the right-hand side, into the material. This is more going towards defect physics, and you can read more about that in these papers. All I want to emphasize is doing that, you can write wires like shown on the right-hand side here into the system by creating point defects on demand. They have about 5 orders of magnitude if you play it right, enhanced conductivity compared to the bulk, and they are stable as shown down here. We tested that for about 2 years. So you now have a model system where you can write these wires where functional domain walls and maybe then work towards the stream regarding the domain walls nanocircuitry. Okay, that's what I wanted to say about mimicking electronic components at the nanoscale. And then I think I started a little later. I have roughly 10 minutes left. Is that okay?
Yes,
Yeah.
please continue. Yes.
Okay, good. That should be then fine for the next, for the last part of the talk. So what I talked about so far is domain walls have specific physical properties. We can mimic electronic components, but the question is, wasn't this a little bit too simple? Because everything was just surface measurements. We looked at the surface, but the domain walls are embedded into a 3D system. What role does the rest of the domain walls play? How can we utilize those properties, and is it possible to access them as well? That's the question I would now like to ask in the last part, because I mentioned at the beginning that we have this anisotropic distribution of all kinds of domain walls, a really complex network. So what does it mean now when I inject a current? I always showed you now lines on the surface and it looked very clean. But in reality, if I inject a current into a network like this, it's highly non-trivial what domain walls contribute to the signal, where does the current go, and to what extent do changes in this complex network matter the domain wall conductivity and therefore matter for the conductivity and functionality. So that was a question we asked ourselves over the last 2-3 years, and we tried to access that and measure it in a little more detail, because so far the only possibility to measure 3D domain wall structures was optically. You see Cherenkov second harmonic measurements on the left-hand side and second harmonic generation measurements here in the middle on two systems, you see that you can nicely image the 3D domain structure. The problem is that the resolution limit is about 1 micrometer, but all the effects we're interested in, these small kinks of the domain wall, changes in curvature, happen at much smaller length scales. So far, it was really kind of like shown here on the right-hand side. We access the surface by experiments, but what's really happening within the system, that was mainly theory territory, because in DFT calculations, you can see, of course, what's going on, what role defects play, but accessing that at the right length scale, at the nanometer length scale in 3D was a true challenge. So we set out to use focused ion beam FIB tomography to FIB through our material and image the domain structure in 3D and the domain wall transport. So you use a focused ion beam to cut the material, then you image it with with secondary electron microscopy, then you cut again and away something, image again. So you do cut and slice and thereby make your way through the material. And that really works. What you see here is now an image SEM on a non-polar surface of erbium manganite. So the polarization is lying in the plane, and you see what we've seen before, these meeting points. And now we are milling through the material step by step, and you get an impression of the 3D structure of the domain walls. So that's now exactly what I mentioned before. You cut and slice, and thereby, maybe we can do that again, cut and slice and get now a 3D impression of what's going on here. Movies like this look great, but of course we have to analyze the data afterwards. You can then use these image stacks and reconstruct the 3D distribution of the domain walls. What you see here is a voxel resolution of 5 by 5 by 25. So we did not really push it here. What you can actually achieve is something like 2.2.5. But you get an idea already now of what's possible. We do not just see the surface structure. We see also vortex structures, bent domain walls hidden under the surface. And that now can be analyzed, and we can really say something about the transport properties in these networks. On the left-hand side, this is to convince you that with SEM, if we have the right parameters, we measure the same as with CAFM. So we have access to the conduction properties. You see here what's a bright wall in CAFM with enhanced conduction, also appears bright in SEM. Then we have even these curved walls and shade features, and you see the very same is appearing in the CAFM. So you can normalize SEM measurements by CAFM so that you have information about the current signals and what contrasts means. And once you have that, you can then mill through the system and really get layer by layer information about the structure and then reconstruct the 3D nature. This is so cool because what you now have available is the charge state. We know how the charge state of the domain wall changes into the depth. And in addition to that, we get information about the conductance encoded in the SEM intensity. So we now have an opportunity to measure charge state and conductance within one and the same experiment at the same time with nanoscale spatial resolution in 3D. And that's really amazing because everybody already knew that charge state and conductance are correlated. This is how you calculate the bound charge and at the wall and then say, oh, we have enhanced or reduced conductance. But really measuring that is a completely different story. And here you now see that it nicely fits when we have a charge state changing, the conduction changes, and if we go from head-to-head to tail-to-tail walls, we go from conducting to insulating walls. So all this matches really nicely, and now we can also understand much more subtle details. We played this game even a little further. We were cutting little cubes out of our material using the focused ion beam, and then performed PFM and CFM measurement on top. This was just to be sure that currents are not flowing somewhere through the material. In a setup like this, you can be sure there's only the cube. Everything has to go through this structure we know, and there's no escape from that. So again, we then milled through. We got the 3D structure, and then we compared the charge state, which you can now get in 3D. You do not just see the surface orientation, you also know how it bends into the depth. And then we, for example, looked at the charge state for these 3 walls. And you see that they have all the same orientation with respect to the polarization. There's not much of a change, but the conductance here is high and here it's low. You cannot explain that from surface measurements alone. But if you take the full 3D charge state into account, you really see that the charge state for the 3 walls is substantially different, and it scales in the same way as the conductivity of the walls. So how it bends into the depths co-determines what you measure on the surface, because that, of course, also determines the charge state. So with this, we now have an additional degree of freedom, orientation into the depths, and that allowed us then to map out and simulate how currents really spread within these networks. What you see here now is an illustration of the really measured 3D state and how a current would spread in this network, where we measured the charge state and then simulate how the current spreads. So you can get a much more realistic picture of what's going on right now. And most importantly, you can also get some numbers out of this. For this, because it's quite important to know, does all this structure here in the depth still play a role or not? Is it important when we look at the top? We already know now that the inclination angle plays a role. For this purpose, we simulated what's happening when I have a domain wall that suddenly stops, and then I make it longer and longer and longer, and see how the injected current evolves. And you see that in the beginning, it has a huge effect, but at some point, the injected current saturates. So it doesn't matter anymore if I go beyond 100 nanometers. It doesn't matter much if the domain was longer or shorter. Everything that's happening and what you're probing with CFM is occurring in a region of about 50 nanometers away from the surface. That is the decisive area that determines the properties. So now we know how thick to make a material when you want to go for a device with this one. Everything beyond 50 nanometers doesn't matter at all anymore. This is the key area we have to focus on. And within this area, we then also compared the effect of having different curvature radius. A wall that is not straight, it can be convex or concave. And you really see that this has a huge impact. The conductance varies by several percent. So it can be 4 times higher for convex and concave walls, what's shown here. So you see on the x-axis, we're changing the curvature radius, and then you see the effect on the domain wall conductance. So it matters a lot if the wall is curved, in what direction it is curved, and all this contributes to the conductance. We then also ensured that the regime here, 50 to 100 nanometers, is really what we have in our system. So Brian Yu and his team did some 3D AFM measurements. They milled through the system, and from that we extracted the curvature radius of immersion walls. And you see there's really a large amount of domain walls in this relevant regime. So for them, we have to take into account if they are bent, in what direction they are bent, and that allows us to control their conductance. And you can really then do correlated microscopy. Here you see 3D images from SEM, FIB tomography, 3D reconstruction, SEM, where you see surface contrast, CAFM. So we now really have the full story together, measuring the conduction properties, understanding the 3D behavior, and the impact of curvature effects. And I think that is really exciting, because that means that we can now really change domain wall conductance by just bending it a little bit, but keeping it in position. We can get continuous conductivity changes at the domain walls without moving them anymore, and maybe even more subtle walls. And this is a summary of my talk. I hope that I was able to convince you that improper ferroelectric domain walls are really exciting, because they give unusual electronic states. We can use these walls to mimic the behavior of electronic components. I showed the example of a digital switch, half-wave rectifier, and that it's now also possible to image them in 3D, analyze their physics. And I think this is really nice progress from what I showed you in the beginning, 1960s, where they visualized the domains in optical measurements. And nowadays we can do that with nanoscale resolution, fully in 3D, and thereby explore the electronic properties of these domain walls, understand the physics. And all I've showed you here was, of course, on our model system, but you can expand that to other materials with domain walls the future. And if you're interested in reading a little bit more about this, these are the main papers I discussed today. And with that, I would like to thank you one more time for having the opportunity of sharing some of our results here. And it was really my pleasure to give this talk, and I'll be happy to answer some questions. Thank you very much.